Hello everyone, so I'm Avishka and today I will be presenting the paper High Resolution Image Synthesis with Latent Diffusion Models, which is commonly known as the Stable Diffusion. So this was published on CVPR in 2022 by these people. So yeah, so moving on. We will first look into the research line and the method, and then see the results of this implementation. So first the research line. So before we dive into stable diffusion, actually it is mostly based on previous work. So when we cover the previous work, most of the, actually almost 80% of the content would be covered of the paper. So these are actually the related work. So generative models. So that means we use a model to generate images. So initially people used GANs, that means generative adversarial networks. So I think we have discussed it within this group, and then came variation autoencoders and also auto-regressive models. So variation autoencoders, basically they encode an image into a variational space. So in the normal autoencoder, what it does is it encodes an image to a single point, but variation autoencoder does is it encodes the image to a distribution. So after that, the decoding will be done from by sampling from that distribution. So by changing the sample point within the distribution, we can do image generation. And autoregressive models, we'll come to that. So I'll cover that for a little bit, and then comes the main paper, the main contribution for this paper, which is diffusion probabilistic model. So and then there's the other part, there's two-stage image synthesis. So when you see the name of the paper, image synthesis in the latent domain. So that means we do not do the image synthesis in the pixel space. We actually encode the image to a much low resolution dimension, a more compact dimension, and do the generation in that compact dimension, and then bring it back to the pixel space. So in that research line, there were these two are the directly related papers for the stable diffusion, which is the VQ way and the VQ GAN. So VQ way is a variation autoencoder based on vector quantization. So I'll come to that part. So we will be covering that part. And the VQ GAN is also an autoencoder which has a adversarial part. So it has adversarial loss. So once again, it is also a vector quantized method. So actually, this paper is also by the same author. So the authors for the stable diffusion are from, I think, Heidelberg University from Germany. So the VQ GAN also was from the same people. The supervisor was the same. His name was Björn Ommer, I think. John, I don't know how to say the name. The name is Ommer, however. So in this section, we will first look into diffusion probabilistic models, which is to be specific, we will be looking at the paper Denoising Diffusion Probabilistic Models by Jonathan and the people, which was published in NeurIPS in 2020. And then we will be looking into VQ GAN. So the name of the paper is Taming Transformers for High Resolution Image Synthesis. So this VQ GAN, the basic difference between the VQ GAN and the stable diffusion is VQ GAN first encodes the image to a latent space and then use the autoregressive model to the generative purpose. In stable diffusion, that in latent diffusion, what they do is they use the same compression model, the same the same first stage model to compress the image to latent space, and then change instead of the ARM, instead of the autoregressive model, they use diffusion model. So the diffusion part will be covered in this way. So I think the path is clear now. And so we'll first look into this paper, Denoising Diffusion Probabilistic Models by Jonathan and the people. So basically, diffusion has two processes. One is the forward process and the other is the reverse process. So the forward process, what it does is it takes an image and add noise to that image sequentially until we get a normal distribution. And the reverse process is what we teach the model. So the model will be forced to learn how to denoise an existing noise sample until it gets a meaningful image. So that is the reverse process. So just take a look at this equation. So you might not understand this directly, but we will come to that. So what we essentially are doing is the forward process. It has a so here the x0 is considered as the image, and xt, that means x capital T, is considered as the Gaussian noise, the standard Gaussian noise. So in the forward process, what we are doing is we take the lower samples, that means x0, and then generate a higher sample, that means x1, using this method. So what this is doing is it outputs xt by using xt minus 1 as an input and as the mean, and beta t as the variance. So this is actually a probability distribution. So what we are doing is we are sampling an image from this probability distribution, and the reverse process is the basically the opposite. So what we'll be doing is we take a noise image, and so this will be a noisy image, and the xt minus 1 will be a comparatively less noisy image. So that is the basic intuition. So we'll come back to these equations once again after we get a basic idea about the basic algorithm. So for that we can see the two algorithms, the training and the sampling algorithms. First we look at the training algorithm. So I will have remove all the mathematical parts for this section. So we will dive into the mathematical part in the coming section. For now, we will just get an understanding what is happening on. So initially we have an image. So actually this is image from the Dream Booth dataset, and then what we are doing is we are sampling a Gaussian noise from a standard normal distribution and sampling T from a uniform distribution. That means we initially decide how many time steps that we will be doing for how many time steps that we will be doing the diffusion process. So for example 250, then T capital T will be 250. So we will be uniformly sampling an integer from that range, and also the noise. And then what we will be doing is we will be scaling this noise and the image of the original image, and then adding them together. These scale factors we will come to that. For now, just know that we will be scaling it, and then we will be getting the noise image. So if this is x0, this will be x1, and then what we will be doing is we will be encoding the T in a sinusoidal way, and then we will be feeding this encoded time and the noise image to our encoder, to our unit architecture. So the diffusion model is actually a unit architecture which encodes and then decodes while having a stick connection. And then this will also produce some sort of a noise. This model will produce the noise. So this noise will be actually the model will be trying to learn the noise that is added to the given image. So and then what we'll be doing is we will be reducing the L2 loss between the added noise and the noise predicted by the model. So in the inference part, we will see how. So you can understand in the inference part, we give a noise sample, and the inference will return another will predict the added noise, and we can subtract the noise and get the image. So that's the most basic training explanation, and then we can see the sampling explanation. So the sampling process, what we are trying to do is we are having a noise image, just a noisy matrix, and then we will be iteratively denoising that noisy image till we get a meaningful image. So we start from capital T. So for example, 250. So we start from the capital T and we go towards 0. So first we will be doing, we'll as usual encode the time step and send through the model, and the model will predict a noise. So this noise will be then subtracted from the initial part. So, and one more thing to point out is the model will not actually predict the difference between this noise and this noise won't be the actual image. So similar to variation autoencoders. So if we compare the autoencoder and the variation autoencoder encodes the image to a single point in the latent space, and the variation autoencoder encodes it to a distribution. So similar to that, diffusion model, what it does is the difference between these two will be actually we can take the difference. So this will actually give a distribution. So the mean of the distribution might look a bit like the mean of that distribution will look a bit like a bit noisy image fairness. But there is also a variational term. So this one will be not actually sample, it will be a distribution. And after that, we will sample from that distribution, and give it here and do the process multiple steps. So you can see here the time when t equals t minus 1, we give the output, and then we proceed the loop until we iteratively get a more denoised image. So for this example, I have chosen t as 5, but in real scenarios, it will be like very large values, maybe 250, maybe 1000. So
you create this animation.
Yeah.
So you record it and upload something.
And then so in this process you might have noticed that in the training process you notice that so we will be randomly sampling the sampling t from the range 0, 1 and capital T. So in that scenario, if we use this the usual forward process, so that means the usual forward process is we have xt minus 1 and we get xt. So if we use that process, we will, so in case we have we got the sample for t as maybe 100, we might in the first glance you might think that we need to do 100 iterations to go to that sample. But actually this can be like using a bit mathematical derivations. We can process this forward process so that we can directly get the xt directly using x0. So this x0 is our original image, and using x0 we can directly come to xt using this computation. And one more thing to highlight at this point is the weights we give to the original image and the variance. So as I mentioned, what we are doing is we are making a noise. We are making a distribution and then sampling from that distribution. So in the forward process, the distribution will have a mean of xt minus 1 multiplied by some constant, and the variance will be the constant pattern. So that way, in different steps, we can either use the same variance and same mean. I mean the same mean for the mean weight, and also we can use a schedule. So I'll show how this schedule affects the variance. So, and this is the weights of here. So you might wonder why we need to have this bt and beta t and root 1 minus beta t and beta t here. So the reason for that is actually we can mathematically prove that when we do this. So if you so if you see this derivation, you can see this there's this alpha bar t term. So when this t tends to infinity, this term will go to 0. This mean term will go to 0 and this term will go to 1. So that means when we have this kind of a relationship in the mean and the variance, we can ensure that the diffusion process will give us a standard normal distribution. Yeah, so that's the forward process, and the reverse process, reverse sampling process will be a bit more complicated to derive. So I'll be instead of explaining the method, I'll be taking this equation as granted. So this is the equation. So we will see how this equation will be used in the actual sampling algorithm. Yeah, and just to emphasize the facts, this beta t is the noise schedule, and alpha bar and alpha t is 1 minus beta t, and alpha bar t is the cumulative product of root alpha t's. Yeah. So this is the reverse sampling process. So the full explanation for this you can see. So in the reference I have included the YouTube video from an Indian person. I can't remember the name. So in that video he is explaining clearly the forward sampling process and the reverse sampling process. So you can look into that. And this is where where the beta value comes. Why we need to use a schedule for beta instead of using the same beta. So if you use a constant beta value, you can. So this y-axis, I'm sorry, I haven't plotted mentioned it. So the y-axis is actually the variance. So that means this term is the y-axis. So you can see here, if we use a constant beta value for all the steps, this will be the value of alpha bar t, and if you use a linear schedule for beta t, so this will be the variation of alpha bar t. So that what it means is we'll get a more gradual noise schedule when we use this linear schedule. Instead, if we have used the constant schedule, if we see the samples and do the forward division process, we can see that we will see that the image will get the noise, and by almost 1/3, if we use the same values, by 1/3 the image will be almost already be completely Gaussian noise. So as a to remedy that, we will be using a linear schedule, so the increase will be more gradual. So this is the actual training algorithm. So as I mentioned before, we will be sampling x naught t. The x naught t will be taken from the image, and then we will be sampling t from this uniform distribution and also noise, as I mentioned, and then by optimizing this over gradient descent steps, we can converge. We can do the training. So this is actually the one that I have mentioned here. So we can get we can do the forward process directly using this equation. So that forward process is done directly here. So we get the noise, we add the noise and ask the model to predict it, and then we reduce the predicted values, the difference between those values. And that is the training process, and the sampling process we have here. So according to the equation I previously mentioned, so that equation is here and other things are here. So if we model this, we can do a good sampling. So, and one more thing to notice is that we will be using this sigma TZ in time steps greater than 1. So if t equals 1, we will not be using this using this noise distribution. So what I mentioned was initially in the simple example slide. So what we will be modeling is a noisy distribution, not a single sample, but a noisy distribution. So this is the mean of that sample, and this is the variance of that sample. So that is what will be modeled by our model. So in the final time step, we can eliminate this noise sample and directly take the mean value as a sample. So yeah, that's it about the diffusion process. And then we can look into the image compression part, which is Taming transformers, also by the same people from Stable Diffusion. Yeah, so this is the basic model. So you can see there is a transformer part here. So this transformer part is the reducing model. So for now, we can forget about the transformer part and focus on the rest of the section. So what we will be doing is first take image, and so you usually know what we in an encoder-decoder scenario, what we are doing is encoding an image and then decoding it back. So the encoded latent space will be a much compact representation of the image. So here what we have is an additional VQ term. So what VQ means is we will be quantizing this this latent representation to a more discrete level, to a more discrete discrete level. So what that will be essentially doing is it will do a kind of a regularization process, and then the result will be much more compact than the normal unquantized value. So for the quantization, the quantization values are actually taken from a discrete code book. So here a single pixel. So here if we have 4 dimensions, this code book will have 4 values for each entry. So in the quantization process, what we'll be doing is we'll be taking this whole sample and then finding the minimum, then finding the code book entry which has the minimum difference from this, and then after finding that minimum one, we will be, it's a usual quantization process. And then we have a decoder. Decoder is the image, and this is where the GAN part comes. So we instead of like the most situation in early approaches, people used to take L2 difference between the predicted image and the original image, and then there are like the other similar matrices like structural similarity. But these people, what they had done is they had introduced they had taken an adversarial approach. So they use a discriminator, a factorized discriminator to discriminate. So here you can see a 4x4 patch grid and to discriminate whether it's true or real. So from there on, it will be a usual min-max loss for the min-max loss. And then there's also another loss called the photometric loss. So we'll come to that part. So hope this is clear. So for the transform part, we'll come later. So here, once again, this is the image, which is HW by 3, and then the code book will be entry. So if capital the capital K will be the number of code book entries, and NC will be the number of channels. So usually it is 4 in stable diffusion implementation. It is 4. And there we have the latent quantized latent space. So this is actually the complete code process. We take the image, we encode it, we quantize it, that means here, and then we decode it. And after that, we have the reconstructed image. So that's it. And then these are the losses we are using it. So as I mentioned previously, we have this adversarial loss, which is a min-max loss, and also this vector quantization loss. So the vector quantization loss tries to learn the distribution of the most suitable distribution for the encoder, decoder, and the code book. And the GAN tries to learn the GAN loss will force the model to learn the all four learnable parameters. Yeah. So hang on with me. This is the one of the most mathematically intense paper I also found. So you might be bored, but hang on. So this the vector quantization loss is they define the vector quantization loss as the difference between the original image and the so this is actually L2 loss. However, and then I don't know why they are doing this one. So what they are doing here is they take the encoded value and the sampled code book and trying to minimize the difference between those encoded values and the code book. But there's this stop gradient operations. So instead of using this stop gradient operations, I don't know why they should have. They might have used encode directly the encoder and the code book to do the backpropagation. I'm not quite sure why they are doing it like this. Yeah. And then the GAN loss is once again the usual min-max loss. We for the real sample we try to minimize this loss value, and for the fake sample we try to maximize this value. Yeah. So minimize this one, so maximize the output of the distribution. And then we have this this meeting term, which is based on based on a perceptual matrix. So I'm not much confident regarding that. So they had actually mentioned another paper for that. So yeah. However, they compute the weight using this method and use it. Yeah. And then so a little bit of the ARM. So I think that transformer part, I think you people already know that from the experience within this group, that what a transformer is doing is it tries to predict the next token. So similarly, once we have when we are using this the original Taming transformer paper, it is an image generation paper. So what it in the image generation part, what it is doing is it predicts this ZQ iteratively, predict the ZQ sequentially and do the generative process. So that's how the ARMs work in this scenario. So it is predicting pixel by pixel of the latent space. Yeah. So when we have the samples for previous I values, we use those previous values to predict the next sample. That means the sample at I value. Yeah. So finally, we can go into stable diffusion. Yeah. So this is the stable diffusion architecture. So you can see here, this is actually that VQN part. So there's an encoder and a decoder, and from here onwards, everything is in the latent space. Yeah. So what we will be first doing is we are taking that latent image, and depending on the T that we have, we can depending on the T that we sample. So the sampling training process is the similar to the one we did, the one I explained in the Denoising diffusion modules part. So it's basically the same. So the only new thing here is you can see this attention heads in this diagram. So they use the attention heads to map conditions to the diffusion process. So we'll see how it's happening in the next slide. So, and one more new thing is this domain specific encoder. So the diffusion process can be controlled using a domain specific encoder. So in the stable diffusion situation, it is an extended. So we take a text input and encode it to a latent space and use that latent space as a condition for the diffusion process. So in the stable diffusion repository, they have shown for multiple doing the diffusion process using multiple inputs. So like semantic maps using depth maps, and there are a few other things. And also using images, we can do the conditioning. Yeah, so that's it. So then we can look into how this attention head is working. So the usual, we are using a usual attention head. However, the new things here is how the Q, K, and V are calculated. The Q is calculated using, so we have this W key, WQ, WK, and WV learnable parameters, and this E theta, tau theta y is the output from the conditioning vector. So this will be a conditioning vector. This will be a conditioning vector, and this one will be simply the value the unit got from its previous time step, not previous time step. The unit got from its previous layer. So there will be multiple layers. This the conditioning vector will be mapped to multiple layers. So they take, if we have two layers, we take, instead of directly passing it to the next layer, we take the input from the layer and do the attention calculation part, and then return that to the next layer. So that is what's happening here. Yeah. So this is so. And few more things to note. The regularization schemes used in this stable diffusion. So they use this scale regularization. So scale regularization is matrix. So it's kind of a normalization. We are if we have a latent representation, we are forcing that latent representation towards another distribution. So in this case, in stable diffusion scenario, they force the latent space to a standard normal distribution. So that's the K regularization they included, and the VQ regularization, the usual vector quantization. But initially in the Taming transformers, you might have noticed that we take the latent representation and then quantize the latent representation, and doing the diffusion in the vector quantized latent space. But in stable diffusion, they do in the unquantized latent space, and the decoder will have a quantization layer absorbed to it. So yeah. So in stable, in contrast to Taming transformers, stable diffusion do the diffusion process in the latent space, not the quantized latent space. And then results, we can see the results. So they have actually shown results for multiple scenarios. So the first thing is unconditional synthesis. So we take a single data set and train on the single data set and get random samples from that trained model. So if we train on a single data set, so for example this CVPR, which is facial images, then that model will only produce facial features, random facial images, random facial images, and same for the other ones. So here you can see we have as the evaluation matrix, we have used this FID score, which is fetched inception distance, as I remember. So this fetched inception distance is actually a loss, so we need to reduce that loss. So what it does is it takes an inception module and get and produce the difference between the features of original images and the generated images. So if generated images are almost equal to the original images, the distance between those two features will be almost zero. So lower the distance, better the performance. So this precision and recall, actually usually we know the precision and recall for classification tasks, but here it is used in another sense. So they have cited another paper from 2019 where they interpret new recall and precision matrices for generative models. So unfortunately I couldn't look into those matrices. However, higher the score, better the performance. So these are the results. Yeah. So in if you see the FID score is they don't score in the FID score, but the precision and control is high here. Precision is high, and yeah. So, and but if you see the images, I think you will get a more understanding that this is performing almost pretty much well. So this was unconditional synthesis, and then we have the text conditional synthesis. Once again, there's this new term, the IS. I think IS is inception score, so something related to the FID, but the inception score is higher the better. FID that means distance, lower the better. So yeah, so you can see that the LDM with KL penalty. This 8 means the factor, the compression factor, and G, I'm sure. Yeah. So this variant of their model is performing the best in the inception score. Yeah, and these are some results from the text conditioning. Interesting things that we can do. And then the other thing they have used for super resolution and also impinging. So these are also results. So they are the latent diffusion is performing very well on these results, and here we can see an example. So this is if we use bicubic interpolation to do the resizing of the image, and this is the LDMSR, that means LDMSR and SR3 methods. So I think SR3 is another benchmark method. So LDMSR, SR3 is a specific method to another paper which focus only on super resolution. So this LDMSR is we are using the latent model for the resolution purposes. And also in painting, they can use the same model. Yeah. So bit about the responsible AI. So I mentioned also this in a informal discussion between this group. So there is an these two were found. I saw these two implemented in the stable diffusion repository. So they are adding in one thing, they are adding an invisible watermark to the image. So that means if we have the image, we can decode that image, and it will contain the text value. So if we like simply do some sort of interpolation or upsample something, that information will be corrupted. However, they are taking this measure to label that this image was generated using stable diffusion, and also they have implemented not safe to not safe for work blocking, work content blocking. So if you try to generate some unsafe content, maybe anything, so the model will actually generate them, and then they had added another encoder to detect those whether that is not safe, and then if they find that it's unsafe, they will simply return an image of it. Yeah, that's an actual implementation in stable diffusion. But if you simply turn off that thing, you probably won't. And yeah, so these are some implementation results. So I saw the code from stable diffusion, and these things. So take an image. So this is from something like for children image tutorial for children. Use this image to generate more samples. So this is image to image task. So and this is another task where a text to image task. So here astronaut riding a bike in a desert, astronaut riding a bike in a in a field and hide the parent variable TT, and Yoda doing base, and load Vader as a cute cat. Yeah. So yeah, that's it. And these are the references that I did. The usual denoising models paper, Taming transformers, and this is the main paper that we were discussing. And also, I found this explanation in YouTube very helpful to understand the diffusion process, the forward and the reverse process. So he's going to all the steps in the process, so you can try look at it. So I'll share the link to the slides also. And also, once again, I have this in my GitHub. You give me a start. And yeah. So then I think we can, and of course, computation leads to the UI operating server. Yeah, so then we can see some implementation.